Good morning. It is 1 o'clock on Halloween, October 31st. The mute is working, everything's recording. That means we can begin. Today we will be continuing on with last week, where we were introduced to three-dimensional forms. As a reminder, a form is the three-dimensional version of a shape. So the classification of a form depends on the form being 1, 3D, and 2, to be a closed form, similar to how a shape must be 2D and closed. Now, some other classifications that apply to shape, such as a regular shape, apply to form as well. Whereas a regular shape is to have all equal sides. A regular form has the exact same, does the exact same thing. So the sides and the angles are equal. So that's the gist. Now, some examples of this would be some of the more popular forms, such as a cube, which is the form, which is the three-dimensional version of a square, a sphere, which is harder to draw, which is the three-dimensional version of a circle, and for triangles, there are several others. But the main regular version of a three-dimensional triangle would be a triangular prism. Or a triangular pyramid. That's what I'm trying to draw. Now, a cube and a sphere are easy because, well, a cube, a sphere, and a triangular pyramid are simple because the components of a three-dimensional form, if you remember, are base, height, and depth. Now the height is simple. All forms have the same height. The depth refers to how far into the page that the form goes into. But the base is important. You can think of the base, at least in this instance, as the shape that is on the bottom of the form. This base refers to, this base constitutes the most important aspect of the form. So what we need to learn is the different names of these forms that are used to classify these forms. For rectangular forms, such as the square, we use prism. And for triangular forms, we use pyramid. I'll rewrite it just in case it's difficult to read. So instead of square, we want to say rectangular. So rectangular, we will put prism. And for triangular, we put pyramid. Now, something to notice about these names is that when describing a prism or a pyramid in regards to whether it's triangular or rectangular, saying it's a prism or a pyramid refers to height. Well, not height, it's the wrong word. The front face. By this, we can refer to, in the instance of our cube, the front facing of the cube is a square. So in this instance, we would say a square prism, because the front facing is a square and the square is rectangular. We would refer to it as a prism. And we would justify it as a square prism. We'll write it up here. Square prism. We say it's a square prism because we said just now that the prism refers to the side of the shape and the square refers to the base of the form. So square base and prism form. And this corresponds to the base and the height in instances, because the base refers to only the bases of the form, while the front facing refers to the base and the height, but mainly focusing on the height. If we apply this to non-regular forms, then we can see where this becomes more useful. And just so we are clear, this does not apply to spheres, because for spheres, all we say is spherical. Or in other words, round. As of right now, spherical or round are the ways that'll make most sense to describe. Because when a shape is round, it's generally symmetrical in a sense. Other ways of writing it: spherical, or round. Another way to describe it is by the name elliptical, where it refers to the form looking similar to an ellipse. But in lower level math such as this, we don't need to worry about ellipses. For now, whenever we refer to a round form, it will almost always be a sphere, and you refer to it as spherical. If you say, if you were to describe a bowl, and you would say the bowl is spherical. So, keeping this in mind, we can ignore the sphere for now and focus mainly on prisms and pyramids. So, one example. One example of a prism would be a rectangular prism where we say rectangle, so we know that the base must be a rectangle. Drawing is not necessarily important for math, but it does make it slightly easier sometimes to see what you're drawing. So as we can see, this is a prism because we know it's not a pyramid. It's prismatic because we can see that the front-facing sides are all rectangular. And it is a rectangular prism because we can see that the bottom of the form is a base in the shape of a rectangle. So if we were to turn the shape over, so it's flat facing, perpendicular, so it's sticking straight out, it would look like a rectangle. And this would be the base. Or in this picture, it looks a little bit more squarish. So this would be the base. And because this is the base, we say it is a rectangular prism. But now, we can take a look at a triangular prism. So we have our form here, a triangular prism. We can see that it is a prism because if we look at the front facing of it, it is rectangular, at least by the front facing of it. That would be the surface area. But the base is a triangle, so we flip it onto its side, so we can look directly at the base, and it is a triangle. It is a prism because its front-facing sides are rectangular. All it is just a bunch of triangles stacked on top of each other, and that is what makes a prism. With the base of a triangle, we say that this is a triangular prism. So quickly write that. Triangular prism. So from this idea, you can generally understand what a prism is. A prism is merely taking a shape, any shape, at least any sided shapes. So as long as it does not have curves. So if we said that this was a sided shape, this would be a pentagon, for instance. We can take the pentagon, we can copy it over and over again, so we get a shape that perhaps, a form that looks something like this. This would be a pentagonal prism, where it is a pentagon prism. So that describes prisms, essentially. You don't have to think about it in terms of having rectangular sides, but it is generally an easy way to remember. But the actual function of a prism is simply that it is any shape stacked on each other over and over again. And that's what you get a prism from. A pyramid works a little differently. So we'll erase these prisms. A pyramid, as you can see, in this case, we have a triangular prism, a triangular pyramid. So a triangular pyramid, as we can see, triangular refers to its base of being a triangle. So base triangle, a pyramid. Now we can understand a pyramid by the fact that its front-facing sides are triangles. If we were to apply this concept to what we've learned so far with prisms, we can see that a pyramid, of course, only has so many sides at its base, but base plus 1. But if we see how it works, on the bottom of the pyramid is its base, so it's a triangle in this instance. But if we look on the top, the very top is just a point. What this means is that a pyramid starts with a base, but as it goes up, you can see that different from how a prism is made from stacking shapes on top of each other, over time, the base gets smaller as we go up a pyramid. So if we cut up a prism and we chop it up into bits, like a loaf of bread, the bases will be the same every time. So if we have a pyramid, let's say that this is bread. If we chop it up to many little bits, we can observe that the bases of the slices that we chop off are the same as the original one on the top and the bottom. A pyramid is different because as you chop up a pyramid into pieces, we can see that the bases get smaller as they go up. So if we draw it as it is, we can see that as a triangle in this instance gets smaller and smaller over time, it does begin to get to a point where it's so small, it does look like a point. And that's why the top of the pyramid is a point, because what defines a pyramid, in essence, is that instead of stacking equal bases on top of each other like a prism, A pyramid is comprised of stacking smaller and smaller, smaller and smaller bases on top of each other until it gets to a single point. If we look at it, if we look at it in terms of the front-facing sides, we have our base at the bottom, and because we and this base can be to any shape, any sided shape, such as, like that would be a hexagon, 6-sided. As many sides as it is, this is true for all sides. As you stack the smaller bases on top of each other, you can see that over time, because the bases get smaller, it looks like a triangle. And that is how a pyramid looks the way it does. So the front-facing sides of the pyramid will look like triangles. Now let's take, for example, a pyramid. Let's say we have a square pyramid. So what we know about pyramids already is at the very top will be a point, and the point will extend down to all the sides of the base. Now, we know that from the name, we know what a pyramid means, and saying it's a square pyramid means that it must have a base in the shape of a square. So we can copy like that. Let's see. And then we copy the corners to the top. A square pyramid, where we can see that all the sides of the square base extend up to the tip of the pyramid. And this is the most famous form of pyramid. In case you have ever heard of the 3 pyramids of Egypt, those pyramids are all square pyramids. Typically, bases that have more sides to them are more stable. So that's why you see more square pyramids and less triangular pyramids. So these two ideas correspond with every single shape you can draw, except for, as always is the exception, a circle. A circle has special conditions for both of them. If we start with the prism, we would not call it a circular prism. We know it by another name. Of circular bases on both top and bottom, if we were to stack many circles on top of each other, we would get the form of a cylinder. We do not call it a circular prism, even though that would probably technically be correct in some ways. A cylindrical, we call it a cylinder, and we can understand that it is merely a bunch of circles laid on top of each other. Now, it does not have sides, very importantly, because a circle has no sides to it. However, what we can do is that if we look at it from the front-facing side, it will still make a rectangular shape. But this will not be a side. This will be merely what shape the cylinder appears as when you look at it front-facing. So this idea is important because it is instrumental to understanding the surface area of a cylinder, and we'll go back to that later. In the instance of a pyramid, we know that the pyramid gets to a point on top and that it has a base of, in this instance, a circle, and we draw all the sides up to it, or in this case, just all the parts around the circle. And this is a cone. Not necessarily a circular pyramid, but a cone. Similarly to how the front-facing view of a cylinder is a rectangle, the front-facing view of a cone is a triangle. But once again, this is not a side, not a front-facing side of the form, because once again, the circle doesn't have sides to it. So these would be imaginary sides that we would look at from front-facing view. But this generally tells you what's happening. We can derive lots of information from the front-facing views of these because we know that to a circle, the area of the circles are pi r squared, and circumference 2 pi r. So if we look at these front-facing sides, we know that these bases of this imaginary rectangle describes the diameter of these circles, because that's the front-facing view. So we can tell that half of this must be the radius, and similarly to this triangle, r. And because it is a front-facing view, the height will be the same as the other heights. So from the front-facing view, we can understand the height of the cylinder and the cone. And correspondingly, we can find this of all of the other forms. So that is the understanding of prisms and pyramids as they pertain to here. And you can apply these same ideas to find the measurements of other forms. So let's erase this for now. Something that we went over last class is the role of surface area and volume. So surface area and volume. As we said last time, surface area is literally the area of a surface. It's indicative of the name. So it tells us the meaning off the bat. Volume is the amount of space that a form takes up. Good afternoon, Mr. Nathan.
Good afternoon, sir.
Mr. Nathan, I have just transitioned into talking about what we were doing last week with surface area and volume. Just before this, I reviewed a little bit about the names of forms, but because I am transitioning into a new topic now, you don't need to worry about this that much, and you can review it in the video. Mr. Deo-chan, it has been a while.
Good afternoon, sir. Sorry I'm late.
You're fine. I just talked about something else regarding the names of forms that we are talking about. So later on, you can review the video that we are recording so far. So last class, we talked about surface area and volume. Surface area literally means the area of the surface of the forms, and the volume describes the amount of space that the forms take up. And volume is indicative of this equation, base times height times depth, which are, if you remember, the names of the directions that we put on our three-dimensional axis. So this would be our depth, our height, and our base. So base describes the amount essentially that the form goes across the screen. The depth refers to going into or out of the screen, and the height refers to the up and down. So if we make a little space here, if we review our regular forms, we have cube, cube, pyramid, roughly looks like a pyramid, and a sphere. As much of a sphere as I can get it. There are some other shapes which we can go over later. A cube, if we start with volume, a cube is the three-dimensional version of a square. So because a square, we found its area to be the base times the height. Could one of you guess what the volume of a cube would be? Perhaps Mr. Nathan?
Sorry, sir. Could you repeat that?
Sure. We know that the cube is the three-dimensional version of a square. Now for a square being a shape, we found how much space it takes up by finding its area. And we said that its area was equal to base times height. If we want to find the volume of a cube in this instance, where a cube is the three-dimensional version of a square, and the volume is the amount of space that a 3D shape takes up, could we figure out what the volume of a cube would be based on how we found the area of a square?
Yes, sir.
What would it be?
Length times width times height.
Very good. Or in this context, we use base times depth times height. Or as you said, at length times width times height. As we have reviewed in the last class, this corresponds to how we wrote our units. So when we described the area of a square, we would say if we use meters, it would be in terms of meters squared. But in the volume of a cube, we would refer to it as meters cubed. And that is where the term squared and cubed comes from. So the area of specifically a square, where this area of base and height would be used for a rectangle, we would say the area of a square is base squared. And the volume of a cubed volume equals base cubed. So we describe meters squared and meters cubed to describe area and volume. That's where the terminology comes from and how we apply it to find the volume of a cube. Now, let's skip over pyramid just for now, and let's focus on the sphere. A sphere is the three-dimensional version of a circle. So circle as it is. Mr. Deo-chan, do you remember the area of a circle?
It's pi r squared.
Very good. So the area of the sphere will be pi r squared. And we all know what pi's come from, and we know that it is radius squared because a circle is a two-dimensional shape, which means similarly to how we write base squared for a square, we write pi squared for a circle. So we never have to, so we only use R to describe our circles. So could either of you predict what the equation to find the volume of a sphere would look like? Do you think that we would use pi?
Yes. Yes, sir.
Okay, good. Because pi is a thing that we commonly use with circles. So we can reasonably guess that we'll be using pi. Now, because we only use R when we describe circles, do you think we will only use R to describe spheres?
No, sir.
You don't think so? What would we use instead?
D.
D would describe the depth. So that's a reasonable assumption. So here's something we can do. We can generally understand a sphere by looking at what you would see when you look at it from the front and what you would look at it from the top down. So here's what a sphere would look like from the front, and here's what a sphere would look like from the top down. So these are roughly equal circles. So this would be the same as this. Now we just said that finding the area would be pi r squared. So because these have the same radius, which we can reasonably tell, these would have the same areas. So if this circle describes the horizontal of the sphere and this part of the sphere describes the vertical of the sphere, and they both use only r, then that means that all three directions use r. Does that make sense?
Yes, sir.
Okay, so if we pretend that these circles, for example, are on a graph, this would be our height and this would be our base. So pretend this is the vertical sphere. And let's say that this is the horizontal sphere. So this is base and this is depth. So this would be the sphere if we looked at it from the top down, and this would be the sphere looking from the front. And these spheres both use radius for both of their directions. So the height uses radius, the base uses radius, and the depth uses radius. So that means that all three directions will use radius. So knowing this, what do you think r will look like in the volume of a sphere? In area. Yes, Mr. Nathan?
Sir, I said I don't know.
That's fine, Mr. Nathan. So as we have it in our area, we wrote r squared because it described the two directions that a circle points, and both of those directions used radius. Because in a sphere, we found that all three directions use radius, we can say that the three dimensions will be radius, so r cubed, whereas all three r's describe each direction. So this is what the volume of the sphere will look like. But just to note, it will look a little differently. Because of the way some calculations work, instead of just pi r cubed, it will be 4/3 pi r cubed. So all you have to do is just remember this little part, 4/3 pi r cubed. But you can understand alone this part that we will use pi because we always use pi to describe the calculations of circles. And we know that because it points in three directions and all of them are r, it is r cubed. And then you have this part on top. So that describes spheres. Is that good so far?
Yes, sir.
Any questions so far?
No, sir.
No, sir.
Okay. So now we can talk a little bit about pyramid. So pyramid is decently simple. The best example of a pyramid would be to use a square pyramid, because that is the most famous and likely the most basic one. The thing about pyramids is that their volume and surface area change a lot on how you find them, depending on what the base is. So it could be a triangle base, a square base, or a circle base, or maybe a pentagon base. The point is that it varies a lot. But to start off with, all you have to remember for a square pyramid is that the volume is base times height times depth over 3. It's as simple as that. Now, we don't want to just know what the volume is. We want to also understand a little about how we got there. So one thing we want to do is look at the area of a triangle. So the area of a triangle is, Mr. Deo-chan, would you happen to know?
Half base times height.
Very good. Half base times height. So this is what we start off with. So area is base times height, and we know that is base and height describing two directions, and we half it because a triangle is found by taking half of a square. So if we, for instance, took this square of area base times height, as we did before, we can cut it in half and find that it makes triangles. So we take this area of the square and we cut off a half of it, and that rest of the half is the area, so the triangle. Similarly to this, we can transfer this idea over to the volume of, at the very least, a square pyramid. So we know that there is some geometry that told us that it must be half of the square. There is probably some geometry that makes, instead of being a half, will be 1/3 in this instance. But similarly to how the formula for a triangle is similar to a square, a pyramid will be similar to a cube by also being a product of base, depth, and height. So it will be similar to that in this sense. Now, it varies a lot, at least when you talk about other bases. So I don't really expect you to memorize the volume in the volume of a pyramid. So volume of a pyramid, if it has a triangular base, for example, will be a volume of 13 times the area of its triangle base times height. But what we can tell is that this is similar to the square pyramid in a sense, because if we look, it uses area times height, and the area of the base of the rectangular pyramid will be comprised of base and depth. So in the end, while finding the volume of all the pyramids will be different, they will still have an underlying method where they use base, depth, and height, similarly to how a cube does. But depending on what the base is, the constants will be different looking. Does that make sense so far?
Yes, sir.
Okay.
Yes, sir.
Any questions before we move on?
No, sir.
Okay. So now we can talk about surface area. So surface area is far easier than volume. And we don't need to go over all the different forms with surface area because they follow the same general idea. Surface area literally means area of surface, which is entirely self-explanatory. So as of right now, you should already understand how to find the volume, or not the volume, the surface area of a cube. Because a cube is merely a cube is merely 3 perfect sides, and the front of all the faces are squares. Could either of you understand what the surface area of a cube would be? Perhaps Mr. Nathan, would you happen to know?
No, sir.
Mr. Dale-chan?
You would find the area of one surface.
Okay, that's a very good start. So we want to find the area of one of the surfaces. What is one of the surfaces shaped like?
A square.
Very good. So because the surface is a square, what would the area be?
Length times length.
Very good. So either length squared or base squared or base times height. Or in other words, as you said, length squared. So we found the area of one side using our understanding of geometry. So now that we have the area of one side, how can we figure out the surface area of the whole shape? Mr. Dale-chan?
You multiply the area of one surface by the number of sides.
Very good. So how many sides does a cube have?
6.
Very good. So we know the area of one of the sides, and we know that a cube has 6 sides and they're all equal area. So that means the surface area must be 6 times length squared. So that is the surface area of a cube. Very good. So what we needed to solve this problem was an understanding of what surface area is. We know what area is, and we know that it's on the surface. So we can get the idea that all we need to do is find the area of all the shapes on the surface of the form, and then add all the areas together, and that will be the surface area. So we can do this, for example, with a pyramid. Let's use a square pyramid again. So we have our square pyramid, little dot at the top. Okay, so as we did before, we said that all we need to do to find the surface area is to know what sides we're using, know the shape of the sides, and add all the areas together. So, would anybody happen to know how to start this?
You first find the area of the square at the bottom of the pyramid. You find the area of that, then find the area of one of the triangular sides.
Very good. Area of the square and area of the triangle. So as we said before, the area of a square is base times height, or in this case, base times depth. We know that the area of a triangle is base times height. Now, we know that the height is the height that we measure from the bottom to the top. But will this base and height be the same as the base and the height of the cube?
I don't think so.
Okay, so being suspicious of this, let's draw out the triangle. So if we take this triangle, we'll move it over here. Here's the triangle we're working with. So we know that this part on the bottom is the base and that this will be the height. Let's start with the base. So this part being the base, this line extends from this corner of the pyramid to this corner of the pyramid. So because it extends to this from this corner to this corner, do you think this base will be the same as the base of the square?
As one side of the square.
Yes.
Yes.
Okay, very good. So we can see that the triangle aligns with the base of the base squared. So this square base, it goes from corner to corner, and we see that this triangle, being all the triangles, lines up with the corners exactly. So the bases are the same. Now we have to look at the height. So if we take the height and we mark the height on this triangle, we can see that the height of this triangle would be a line that travels down the middle. So it goes to the middle of the square and up directly to this point. Does that make sense?
Yes, sir.
Okay, that's how we generally measure it. Now we draw the height of the triangle as it is here. We have to mark the triangle. And if we mark the triangle this way and we were to draw it on the pyramid, we would draw it like this. So the height of the triangle is different from the height of the pyramid. Would either of you know why this happened?
Is the
No,
pyramid?
sir.
Okay. Mr. Deo-chan, what were you saying?
The pyramid is one whole shape. So the
It's a
line
pyramid.
goes down. So the line goes down in the middle, but the triangle is only like one triangle. So it goes down the other side.
Okay.
Nothing, sir.
Oh, okay. So Yeah, because the pyramid is the whole shape, the height goes directly down as it is in the middle. But the triangle, because the triangle has to extend from the base to the point up top in the middle, the triangle is at an angle. So that means that because it's at an angle, the height of the triangle is at an angle as well. So it tips that way, and that's how the height works. So this means because the height has to tip over to be the same height as the pyramid, the height of the triangle will actually be bigger than the height of the pyramid. And the reason why is because it tips over. So this height is fundamentally different from this height. So that means we'll put a little asterisk next to the height here when we say the area of the triangle. Now, if we look, we see that we have our height down the middle for the whole pyramid, and we have our height down to the side of this triangle. And if we were to draw this out, we would see that this would be the first height. This would be the height of the triangle. And let's say that this is the length from the center where the height goes to the outside of the base, where the triangle extends to. Now we can see that we have a new triangle that contains the height of the pyramid, the height of the triangle, and this length here. And we can see right here that this length is half of the length that extends across the whole square base of the triangle. So that means this would be half of the base. So if we were given only the height and only the height of the pyramid and only the base side of the pyramid in this instance, do either of you remember an equation that allows you to get the third side of a triangle from two sides?
No, sir.
Okay. So let's say that we have our three sides here. Let's say that this base is A. Let's say that this height is B. And let's say that this height is C. We need an equation that we apply to a triangle such as this, where we can use these two, the A and the B, to find the C. Fortunately, we do have an equation called Pythagorean's theorem. And this equation is A squared plus B squared equals C squared. Does that look familiar? Either of you? Mr. Nathan, I think
No,
your sound is
sir.
off. Oh. Okay. So this is something that I believe we reviewed before, and you might have to check your notes for it, back when we were using just shapes and triangles. So this is something to keep in mind. So in the future, when you're using pyramids, if you have your height and this base, you can find this height here, which you'll need to find the rest of the variables you need to solve for the areas, and then you add them all up. How many triangles are in this square pyramid?
4.
4. So that means you just need the area of one of the squares and 4 of the triangles, and that is the surface area of the whole pyramid. All right. Any questions?
No, sir.
No, sir.
Okay. So that is good for now. We can take a 5 or so minute break until about 2:11. And we will review what we went over today. So at 2:11, we can resume.
Okay, sir.
Okay, sir.